Hi, in this video, I'll present you an outline of linear programming, and this is the fourth chapter of business decision models. In this video, we'll start with the basics of linear programming. Then we'll have an example of modeling a linear program for a decision problem. And finally, we'll solve a two-variable linear program by the use of a graphic. A linear program is a type of model used in solution of a decision problem with high complexity and under the certainty conditions. That means in this chapter, the linear programming is a method used in the condition of certainty. A linear program maximizes or minimizes a linear objective function subject to some linear constraints. Here in the blue frame, we have an example linear program, and this is a maximization. There are two decision variables, x1 and x2, and there are four constraints. At the bottom line of the linear program, here's an expression. This is a closed expression and refers to distinct constraints. One of them is x1 being greater than or equal to 0, and the other one is x2 being greater than or equal to 0. So there are four constraints in here. These constraints are all in the form of inequality. In a linear program, the constraints can be an equality as well. That means these signs could be an equality instead of these. The objective function given in here gives the outcome which is desired to be maximized for this specific linear program. The constraints here are the limitations for the decision variables. In a linear program, the values of decision variables x1 and x2, values of these, cannot be negative, and it's given at the bottom line of the program, and these are called non-negativity constraints, as the values of the decision variables must be non-negative. A feasible solution is a set of decision variables that meets each of these constraints. Here we have a solution 1, and it is -1 for x1 and 2 for x2. This solution is clearly not a feasible solution, as this value of x1 violates the constraints of non-negativity. These constraints are not met, especially we're talking about for the non-negativity. Here we have a solution 2, and it's 2 for x1 and 3 for x2. Let's check this solution if it's feasible or not. What we do here is setting the values of decision variables in the constraints to the values of solution 2. x1 is 2, then 5 times 2 here is 10, plus x2 is here in solution 2, it's 3, so 6 times 3 and yields 18. 18 plus 10, it's 28, and it's still less than 30. That means this constraint is met by solution 2. Let's look at another constraint. Here minus x1, and x1 was 2, so it's -2, plus x2 is 3. We know that from the solution, the value at the solution 3, so solution 2, sorry. 4 times 3 here is 12, minus 2, it is 10, and it's still less than 12. So this limitation of the problem is not violated by solution 2. So this constraint is also met. Obviously these are positive, so non-negative constraints are met as well. So this solution is a feasible solution. If the solution is feasible, Then we can try it out on the objective function. x1 was 2, 2 times 2 is 4, plus x2 is 3 in here, 4 plus 3 is 7. The objective value of solution 2 is 7. Here we have another solution. It's 5 for x1 and 0 for x2. This solution is also feasible. That means we can try the values of the decision variables on the objective value to get the objective value of this specific solution, this specific alternative. x1 is 5, so 2 times 5 is 10 plus 0. The objective value of solution 3 is now 10. When we look at these three, the first one is not considered. This is ignored as it's not feasible. Solution 3 and solution 2 are feasible solutions that can be applied for the decision problem. These are possible alternatives can be applied. And the outcomes of solution 2 will be 7, and for solution 3 it will be 10. Between these, the solution 3 is more favorable than the solution 2 as it has a higher value of objective. As it's the linear program is originally a maximization, we choose with the highest value when we consider two solutions. Here, solution 3 is better than solution 2. However, we don't know that the solution 3 is the best solution. We don't know if it's the optimum one or not. The optimum solution is a feasible solution that reaches the most favorable value of this objective function. Linear programming provides solutions under some assumptions. These are proportionality, additivity, divisibility, and certainty. Proportionality means that all the variables have an exponent of 1. In our example, linear program example here, we look at the exponents. These are all 1. There are no variables in here with a square that is square or that is a square root of a decision variable. They do not exist in this model. All the powers of these decision variables are 1. So this program is modeled under the assumption of proportionality. If there were any decision variables, square decision variables, or a decision variable with a higher exponent, then these expressions would be a quadratic expression rather than being a linear one. The second assumption is additivity. Additivity prohibits cross-product terms of the variables in the expressions. Here in the expressions, we don't have any multiplication of these two decision variables like x1 times x2. There is no there is no variable that is a cross product. The third is divisibility. Values of the decision variables can be fractional. We presented some example solutions, and these values of decision variables are all integers. These values can be also a fraction, such as this can be for solution 2, the value of x1 could be 2.5 instead of being an integer value such as 2. And the last one is certainty. The conditions of model situation is stable, and thus the model parameters does not change over time. I hope you understood the basics of linear programming. Now we can model a linear program for a decision problem. Modeling is a transformation of verbal description of a problem into a mathematical expression. Here, think of a farmer who is trying to decide the productions, plans of productions, and he seeks the most profitable production mixture under the limitations of labor. In this table, there are some alternative plants: tomatoes, cucumbers, and aubergines. For instance, 100 kilograms of tomatoes. In the planting phase, tomatoes requires half day of labor for plowing process. When it comes to harvesting, 100 kilograms of tomatoes require 1 day of cropping process, 1 day of labor for cropping process. And the tomatoes, 100 kilogram tomatoes, are sold in the market with a profit of $6. There is a $6 per 100 kilogram profit for the first alternative. And these can be explained such these for the other one, the other two, cucumbers and aubergines. This is the information table for the decision problem. So we have two procedures for each plant, which are plowing and cropping, and these are limited to the possible workforce. There are 24 days for plowing process, and there are 60 days for cropping process. Possible manpower for this process is at maximum 60. Now we pass on to modeling. Our decision variables here are the production amounts of tomatoes, cucumbers, and aubergines, and these are x1, x2, and x3 respectively. As the producer seeks the most profit, the objective function is a maximization of the multiplication of each product, the multiplication of each production amount, x1, x2, and x3, by their respective profits in dollars. These are the profits of each plant given in the table, given at the last row on the table. And we have some limitations here, which is about laboring capabilities. There are limited days of labor for the processes of plowing and cropping. We can write down two distinct constraints for these two. First is for plowing, and it's the multiplication of each production amount by its requirement of labor given in the table. It's for plowing. It's 0.5 days for x1. We write down it here, plus 2 days for x2 and 1 day for x3. These summation of these three must be smaller or equal to the number of possible laboring days, and it is 24. And for the cropping, we can write down the constraint in a similar approach. It's a multiplication of each production amount by its requirement of labor for the process of cropping. Obviously, we cannot produce something in negative values. You cannot produce negative 100,000 kilograms of something. That means the production amounts, the decision variables, must be non-negative, and these are given in the non-negativity constraint. Now we have formed our linear program by the knowledge of decision problem given above. Let's pass on the graphical solution of linear programs. The linear programs that have only two decision variables can be solved by drawing on a graph. Here at the right hand side of the slide we have a two-dimensional plane. Here each axis represents a decision variable. The vertical axis is for x1 here, and the horizontal axis is for x2. The non-negativity constraints limits the feasible solutions to be on the upper right hand side of the plane. Feasible solutions can only be at the upper right hand side of the plane. For values of x1, let's say in here, can only be positive or can be 0. So the feasible values of x1 can only be in the right side of this vertical lane. Similarly, for x2, x2 can only be positive or equal to 0, so the values, feasible values of x2 will be in the upper side of this horizontal line. So here feasible regions can only be in this quadrant 1. And graphical solutions begins with the determination of the solution space, which is called a feasible region. The feasible region is an area formed by the lines of the constraints. The optimal solution is then determined based on these feasible regions. Here we have the same examples, linear programming examples, or in other words, linear program we have in the blue frame. To solve this program on a graph, first thing to do is to draw the lines for the constraints and form the feasible region to get the optimum solution from this region. So first thing to do is drawing the constraints. To draw the lines of the constraints, inequality constraints, as such in here, must be altered to the form of equality. This must be an equality. And to draw the line of an equality, there is a need for at least 2 points that hold for the equality. Then a line can be drawn based on these points and can be extended throughout these points. Let's draw the line for the first constraint of this linear program, and it's an inequality, so we transform it into an equality form, and it's given in here. To determine the two points, a convenient way is setting one decision variable to 0 and calculating the another. So we set x1 to 0, and the equation turns in the form 6 times x2 equals to 30. From here, we obtain 5 for x2. So x1, when x1 is 0, then x2 must be 5. And this is 1 point we obtained here. Another one is x2. We set x2 to 0, and the equation turns into the form that 5 times x1 equals to 30. And from here, we obtain 6 for x1. When x2 is 0, x1 is 6. Now we have 2 points, and we determine them on the plane. These are the points at the right side of this plane. And now we can draw the line in between these points and extend them throughout these points. This is the equation. This is the line for the equation form of the constraint. However, our original constraint was an inequality, so the next is to determine the feasible region for this constraint, inequality constraint. What we do here is choosing a reference point, and a reference point tested on the inequality for this line to determine which side of this line is the feasible region. Our reference point is origin for convenience, and origin zeros for x1 and x2 holds for this inequality as 0 is less than 30. And the origin is the point resides under this line, so the feasible region for this specific constraint is here, the shaded area, this blue area. This is the specific feasible region for only this constraint, this one. We can also form the feasible region for the next constraint, and if we do the calculations, the region will be something like this, given in the plane on the left. The intersection of the shaded areas for these constraints forms the feasible region of the linear program, of the whole linear program. Our linear program consists all these two constraints, so the combination of these two gives us the feasible region. Here, this is one of the constraints line. This line is for the second constraint, and the green area is the feasible region for the whole problem. The optimum solution is at one of the corners of this feasible region. We don't know yet, but we can calculate each corners and choose the one with the highest objective value. Corners can be calculated by solving the equation pairs of the crossing lines. This one is for this lane. This is the equation. For this line, the equation is given here. When we solve these together, you'll find the values of point A, for instance. To draw now to get the optimum one, instead of calculating each these corners and selecting the highest, the one with the highest objective value, we can draw isoprofit lines. Isoprofit line is a line that has the same slope with the objective function given in here. This has the same, and the values on the same line have the same objective value. Their objective value, the points on the same profit line have the same objective value. For instance, for isoprofit 1, L1, it is about 7. We can draw a lot of many number of isoprofit lines with the same slope. When the drawn line, isoprofit line, goes further to the right, the objective value of it increases. You can see that L1 has about 7, whereas L2 has about 9, and the furthest one that has a intersection with feasible region has an objective value of 12. To find the maximum among these corners, we draw the farthest isoprofit line that is a corner on a feasible region, and here in this problem it is corner C with the values of 6 for x1 and 0 for x2, and the objective value is 12. This is the optimum solution, this obtained by a graphic, two-dimensional graphic. The contents of this chapter may be a little bit confusing, so what I recommend you is to read this chapter on your book to get a full understanding over these topics. Hope to see you in the next videos.